So, hi students, let's start new chapter which is hydrogen. Okay, chapter number 9, unit 9, hydrogen. Okay, so the hydrogen, what is hydrogen? Hydrogen is the first element of the periodic table. Okay, it is the first element of the periodic table. Its atomic number is 1. Its atomic number is 1. It contains 1 proton and 1 electron. Okay, 1 electron, and it does not contain any neutrons. So its electronic configuration is written as 1s1. Okay, its electronic configuration is written as 1s1, and it is one of the unique elements present in our periodic table. It is one of the unique elements present in our periodic table because still its position is not been confirmed. Okay, due to its unique nature. What is the unique nature? The unique nature is that the hydrogen has resemblance of its property like that of the alkali metals also, and sometimes it behaves like that of a halogens also. So it is a very big matter of discussion that where to keep the hydrogen in the periodic table. In the Mendeleev's periodic table, hydrogen was kept with the halogen groups. Okay, but in the modern periodic table or Moseley's periodic table, it is kept with alkali metals. But still, it is a matter of discussion. Because the unique nature of hydrogen makes it more contradictory. Okay, makes it more contradictory where to keep it. Now, why it is kept with alkali metals? Okay, we will tell you why it is kept with alkali metals and why it is kept with halogens. What is the reasons behind it? We will tell you here. So the first reason is electronic configuration. So according to electronic configuration, if I am saying, then it is 1s1. Then the sodium's electronic configuration comes out to be 1s1, 1s2, 2s1. Then potassium's number comes 1s2, 2s2, 2p6. Okay, sorry, here lithium, then sodium. Okay, 1s2, 2s2, 2p6, 3s1. Then potassium comes 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. Okay, so here we can see that it is matching with the electronic configuration in outermost valency with the alkali metals. Okay, alkali metals. Next, due to this reason, due to presence of one electron in their outermost shell, it is electropositive in nature. Also its valency is +1. Okay, and when it combines with electronegative elements, the combination with electronegative elements of hydrogen is similar to that of the alkali metals, such as when hydrogen is combined with halogens, so it forms HCl or HBr. Okay, similarly lithium also forms like this only. Sodium also forms these kinds of compounds. Okay, so this is the resemblance which are matching with the hydrogen and the alkali metals. This is the resemblance of hydrogen's property matching with the alkali metals. Okay, also when liberation at cathodes is done, okay, in electrolytic process, in electrolytic reactions, if I am taking NaCl as an electrolyte, here we will get 2Na plus Cl2. Okay, so if I am taking 2HCl, here it will always H2 plus Cl2 will be released. H2 plus Cl2 will be released. So if I am saying about the electronic configuration or the electropositive nature or the valency or the resemblance of forming compounds with the electronegative elements and also the electrolytic reactions, all these are matching with the alkali metals. All these are matching with the alkali metals. So its position with alkali metals is not wrong. Its position with alkali metals is not wrong. Now coming with the halogens, why it is kept with halogens? Why it is kept with halogens? First thing, why it is kept with halogens? So electronic configuration. For electronic configuration, as it is having only one electron in its outermost shell, okay, one electron in its outermost shell, and it requires one more electron to complete its duplet. Okay, hydrogen and helium are only the elements in the periodic table which are satisfied by the duplets, not by the octet rule. Okay, they are satisfied by the duplets only, means one more electron is required to complete its duplet. Okay. Similarly, if I am taking fluorine, its electronic configuration is 1s2, 2s2, 2p5. Chlorine, 1s2, 2s2, 2p6, 3s2, 3p5. So all these are also requiring only one electron to complete their octet, or to complete their valence shell. Okay, to fill up their valence shell. Next is the ionization enthalpy. Okay, next is the ionization enthalpy, whose hydrogen's ionization enthalpy match up with the ionization enthalpy, match up with the halogens. Okay, what is the ionization enthalpy? The ionization enthalpy is the energy which is required to form the ions, Okay, so the ionization enthalpy of hydrogen is 1312 kilojoule per mole. Okay, while that of halogens are, for fluorine it is 1680 kilojoule, for chlorine it is 1255 kilojoule per mole. Okay, so this shows that the hydrogen is very near. In terms of ionization enthalpy with the halogens. Okay, this shows that the hydrogen is very near with the halogens. While if I am saying for lithium and sodium, so the ionization enthalpy for lithium is 520 kJ per mole. For sodium it is 496 kJ per mole. Okay, so we can see that in terms of ionization enthalpy, it is not matching with the alkali metals. It is more nearer to that of the halogens. Then next is the electronegative character. So I have told before only that due to presence of 1s1 and s orbital as its valence orbital, it requires only one electron to gain and become a stable one, or to complete its electronic configuration. Okay, so it is also having a electronegative nature. It is also having a electronegative nature of -1, which is present in halogens. Okay, so electronegative nature same as halogens, which is -1, Okay, next is the oxidation state. When I am considering hydrides, such as Na, then it will be -1 here. Okay, and if I am considering NaH and if I am matching it with NaCl, then both halogen and hydrides and halides are having -1 valency. Okay, the last one is the liberation at anodes. So at anode we will see that H- is liberated, and at anode Cl- is liberated. So hence at liberation at anode or electrolytic reaction is also same for that with halogens. Okay, so hence there is a very big contradiction with the position of the hydrogen. It resembles some of the properties like alkali metals, and it resembles some of the properties like halogens. So in which group we have to keep it? In the first group or in the 17th group? It is one of the bigger questions which is unresolved, pretty bit unresolved, quite unresolved presently also. It creates a great confusion in the minds of the chemist where to put the hydrogen, okay. So next, what is the occurrence of hydrogen? Okay, we have to see what is the occurrence of hydrogen. So for occurrence of hydrogen, we know that hydrogen is occurring. Okay, next moving with the occurrence of hydrogen. So hydrogen is one of the most abundant element of the universe. Okay, about 70% of the universe is made up of hydrogen. How much? About 70% of the universe is made up of hydrogen. Okay, and if I am considering about the Earth's crust, it is about third most abundant element on the Earth crust. Okay, it is the third most abundant element on the Earth crust. With carbon, it forms hydrocarbons. Okay, you know that with carbon it forms the hydrocarbons. Okay, which are the base of the life. On Earth. It also constitutes 15.4%. Okay, how much? 15.4% of the Earth's crust and ocean. Okay, ocean is what? Water, and water means what? Hydrogen. Two molecules of hydrogen when reacted with one molecule of element of oxygen. When two atoms of hydrogen are reacted with one atom of oxygen, then it forms water, and this water forms the oceans. Okay, and also some of the hydrocarbons which constitutes the Earth's crust. Okay, so it is 15.4% of the total Earth crust and ocean. Okay, but there is a reason that in atmosphere we does not find hydrogen in huge quantity. The reason is that hydrogen's lightness, okay, it is lighter in weight. So due to this reason, it is very hard to retain it in the atmosphere due to low Earth's gravitational pull. Okay, the gravitational pull of Earth is not enough to retain the light hydrogen in the atmosphere. So hence we do not find large amount of hydrogen in the atmosphere, but hydrogen's presence is in the Earth's crust in very large amount, about 15.4% on the Earth's crust and ocean, and also it is the third most abundant element on the Earth's crust, present on the Earth's crust. Okay, let's see the isotopes of hydrogen. So there are three isotopes of hydrogen. One is the protium, deuterium and tritium. Okay, so how we can distinguish these three isotopes of hydrogen? So the first property on the basis of which we are going to distinguish it is the symbol. Okay, so the symbol for protium is H11. Okay, or simply it is represented by capital H, while the deuterium is represented as HD12 or capital D. Similarly, tritium is 13T13 or capital T. Okay, capital T. The atomic number for all the three are 1, 1 and 1, because it is the isotopes of hydrogen, no? So the isotopes are the elements whose atomic numbers are same, but the atomic masses are different. Then comes out the mass number. So the mass number for protium is 1, for deuterium is 2, and for tritium it is 3. Okay, relative atomic mass. What is the relative atomic mass? So it is 1.0078. Okay, which is considered nearly about 8, so 1.008 it is taken. Next, 2.0 3.141, okay, for deuterium, and for tritium it is 3.0164, okay, 3.0164. okay. Moving further, relative abundance. So the relative abundance of protium is about 99.99%, okay, it is about 99.99%. then for 99.98, take it 99.98, okay. Then for deuterium it is 0.015, and for tritium it is 10 to the power minus 15%, 10 to the power minus 15%, okay, 10 to the power minus 15%. Nuclear spin for sorry, protium it is 1/2, for deuterium it is 1, and for tritium it is 1/2, okay. Quantum number is 1/2, 1 and minus and 1/2, okay. Quantum numbers, nuclear spin quantum number is 1/2, 1 and 1/2, okay. And radioactive stability, and for radioactive stability the protium is not stable, okay, they are unstable in radioactive conditions, okay, they are unstable in radioactive conditions, sorry, they are stable in radioactive conditions, and they are non-radioactive, they does not give any radiation, okay. The deuteriums are also stable and they are non-radioactive, means no radiation will be seen, but tritiums are radioactive in nature, therefore their abundance is very low, due to their radioactive nature. They readily become some other element due to their radioactive nature, and its half-life is 12.33 years. Its half-life is 12.33 years. Means certain mass of tritium is taken. If a certain mass of tritium is taken, then to depletes its half mass, it will take about 12.33 years, okay. So these were the isotopes of hydrogen and their distinguish difference on the basis of the different properties of the isotopes of hydrogen. So we are taking today's class up till here only, and we will continue this class in the next session, okay.